All right, so we're solutions minded, and one of the things I want to talk to you about is, well, what do you do when there's a problem? And I need to just, I don't know which button direction to go here. There we go. So, one of the things that we have been hearing a little bit about that we work here at Columbia with Missouri Breaks and your communities is there's a common problem with arsenic and uranium in water. This is not a problem limited to the Pine Ridge, but it's certainly something that affects us here a lot. What do we do about that? Well, one of the things that you've heard about from earlier was a success story, right? Water is getting better, largely reflecting the fact that we're switching to other water supplies we have other options. The best thing you can do if you've got bad water is use different water. Sometimes that's not an option though, and we have to think about treatment. And so where our group has come in is trying to understand how we can develop treatment alternatives that would clean water for both arsenic and uranium. Turns out that's hard. Hard because, well, almost anything can be treated, I'll call it easy in quotes. It's like easy when you're the professor and you don't have to do the work. But it's actually hard to maintain. Oh,
that's for internal recording.
Oh, sorry, here, we got multiple things to keep track of. Dropping the ball as usual is what's happening. So, you know, when we have these pollutants, we can treat them, but it's really hard to keep those water filters working. And very commonly, even if you have a good system, it's not working. And so we are trying to develop a better system. Sorry, I keep going the wrong way here. Now I have this. Our approach is to use iron, basically the things that are naturally in our water, the bacteria that are naturally in water, that are doing good things. We think of bacteria often as bad, but we're going to talk about how they can do good things. We're going to think about how they can make absorption materials so that those contaminants stick to them. Just like water gets cleaned as it goes into the ground and goes through to a well, we are going to try to capture that kind of chemistry in a water filter so that it works and can be recycled. Now, one of the things that happens when we've done that water filter research over the last 5 or so years that we've been doing is we've learned that it doesn't always work, right? Water filters, just for all the reasons that we don't have great water filters, especially for uranium, there's a balance. You want the flow to be fast enough through the filter that you can get a lot of water when you need it, but if you make it go too fast, things don't work. And so this is just a graph of some of the laboratory data, and it really points to something that's really key. As a chemist, I think, oh great, I can do all kinds of things in the lab, but this is a good example of there's no substitute, like working with our community members to be able to actually see how things work in practice, because our water is different in our own wells from what I can make in the lab, and making water in the lab that sort of emulates Pine Ridge water is quite hard. So actually one of the things we're trying to do is actually test these water systems in the field, in homes, with water, with wells that are actually contaminated and make sure they work. Because we would never want to recommend doing something if it's not going to be, dependable, we'll call it, and sustainable. So that's called a pilot test, when we want to take our design that we spent years on and sort of distill it down into a system that we can go work on and actually use it somewhere in the field. And so that's what we're in the process of doing. I just want to give you a little update on how that's gone. We recently put our first pilot test in. We did it because it's near to New York. We did it in New Jersey. Still relevant in the sense that this is a well that has both arsenic and uranium in it, much like our systems here. And it is the system here. Oh, sorry. There we go. It's a simple system, basically, where you can see it there in the front. It's in front of a whole bunch of other water equipment that's being used at this house because they have uranium in their water, they have arsenic in their water, they have radon in their water, and they have radium in their water, all of which have water treatment systems attached to them. And this little system in the front here is designed to sort of think of it as a replacement for that. And I want to show you some of the data that has come from doing that. Initially, so the reason we're doing this is we want to make sure these systems work. We don't want to optimize it. And one of the things that we've noticed as we start to measure things, it's a complication I think is really important to point out, is these are just repeated measurements of the same well for a month. That's not changing again. Oh, sorry. Now I have two screens doing different things. It's not a good idea. One of the things that happens is, if you notice, the arsenic concentrations are relatively constant in the well over the course of that month, but the uranium concentrations vary significantly. What's happening is, as this well turns on and off, pumping water into the house, it is literally changing what water it's accessing when it does so, and that composition is really changing. This is complicated figuring out how our water system is working, because it means you have to have data for each moment that we are trying to test the water system to compare to. We've also done another little small-scale pilot, very short, that shows how arsenic concentrations and uranium concentrations are remediated. The system is working pretty well for arsenic, but it requires a little bit slower system flow to be effective for at least this system here. So one of the things I'm doing for the systems we're trying to implement here over the next few weeks, we're really close to doing this here in OST, is to figure out, have designed the system so that we can both achieve enough flow for uranium removal and arsenic removal at the same time. What I want to now switch to is give Sara Attfield a chance to talk about the natural microbes that are naturally found here that are responsible for that transition.
Nice. Thank you for the introduction. So yeah, my name is Sara, and I'm actually from England, and I came here yesterday, so I could talk to you about natural microbes in the OST and how we can use them to treat water. So people have already talked a bit about this, but I thought I'd just quickly go over it again. We can use iron bacteria to remove heavy metalloids from groundwater, and I'm interested in photosynthetic iron oxidizers. So these only really need energy from sunlight to photosynthesize, and they oxidize iron 2 to iron 3, producing these minerals that are really good at acting like a sponge. They absorb heavy metalloids from groundwater. And this would work really well in groundwater wells because they could be encouraged. They already naturally live in those groundwaters. And we can encourage them in bioreactors that can work at point source and would be really a cheap way of cleaning water and with no maintenance. So I've been working with these bacteria in the lab. And they look like this. They have a rod shape. They produce these minerals, which are sponge-like. So iron is the fourth most abundant element in Earth's crust, so we tend to find iron bacteria everywhere. And they tend to live in zones. They tend to live in zones, and they often control heavy metalloid concentrations in groundwater. So we tend to find iron oxidizers near the surface of water columns and sediments and iron reducers at further depths, and these can influence uranium and arsenic concentrations. And one way that we can track where these microbes are in the environment is using genetic analysis. So I wanted to see the spread of iron oxidizers in the OST and also look for bacteria that could be influencing uranium and arsenic. And I did this by measuring the chemistry at 12 households in the OSG. And then I extracted DNA, and I did analysis that tells me who's there, so what type of microbes are there, and what can the microbes do. And what we found is iron bacteria tend to follow iron concentrations in groundwater. And it was really encouraging to see at some of the sites we see more than 10% of iron oxide is already naturally living here. So they would work really well in our bioreactor systems that Ben has been developing. So here they are in red. And in one of the sites, we even detect some of the genus that are from the same model strain that I've been working with in the lab. So it's really reassuring to see what I've been doing in the lab is what we are really naturally seeing in the environment here in the OST. And we also can look at these genetic analysis, and in the OST we can see metabolisms for uranium reduction, such as this MAC-A gene. There's quite a high potential for uranium reduction across all of the sites. And we also see a high potential for arsenic redox genes, which could be really important for how we see arsenic in the groundwaters. So, thank you very much.